All right. Welcome everyone to DDPS seminar today. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions during the talk. But otherwise, if you want to be, if you don't want to interrupt the presentations, you can use chat room and post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Let me introduce our speaker today. It is an honor to host Dr. Kyungmin Yeo, who is a research scientist at IBM T.J. Watson Research Center. He received a PhD in applied math from Brown University in 2011. Before joining IBM and research in 2013, he was a postdoctoral fellow at the Lawrence Berkeley National Lab. Dr. Yeo has been working on a range of research areas from soft matter physics to atmospheric sciences. Since joining IBM Research, his research interest has been focused on hybrid physics statistics, models, and deep learning for random dynamical systems. Today, Dr. Yeo will talk about reducing data resolution for better reconstruction, super resolution of Navier-Stokes flow. I'm sure we are going to hear a wonderful talk. Now, let me before I pass the baton to the Dr. Yeo, let me ask somewhat informal questions to get to know him better. I know you like to travel with family, and happens to know that your wife is, some artist
Yeah,
job. If you can share the most favorite the place you have been so far, and tell us why.
yeah. So it's more like so my spare time is mostly devoted to helping out my wife, and she's actually a painter, but she also does photography and so on. So we kind of most interesting places we traveled were Iceland. So we went to Iceland like 3 times, or in the winter, so that you don't really get interrupted by any other people. So it was quite fascinating. If you go Iceland in winter, always be prepared, because sometimes things can happen. One time, the first time we went to Iceland, then we actually got stuck in a mountain and stayed the night in the car. And the next day we walked down the mountain to get rescued. So it was a very fascinating place to us. So
Was it because of the snowstorm you
yeah,
got
yeah,
stuck?
because of snow. We rented a small car which couldn't move. So I tried to shovel it out, but it didn't work. So yeah, next day we walked like 3-4 hours to find a farm and get rescued. So
Oh my goodness, that sounds devastating.
it was interesting.
It was interesting. Okay. Well, thank you for
At the
sharing.
time though.
Okay. Well, thank you for sharing interesting story. Okay, the floor is yours.
Okay, great. Thank you, Dr. Che, for the introduction and the invitation. So I'm Kyungmin from IBM Research. The topic I'm going to talk today is mostly about like a good old-fashioned state estimation problem. But here, the interest is that when we use super resolutions, sometimes we can get a better reconstruction of the ground truth state, particularly when the data is noisy. So this is the joint study with my collaborators, Maggie, Mike, and Segi. So in this study, we almost all contributed equally. Maggie mostly did the numerical simulations, and Mike and Segi were responsible for the theoretical derivations. I just did a little bit of everything. So this is actually motivation of the study. When you have some observation of physical phenomena, it's very difficult to get away from corruption. This is one example how they actually measure the fluid velocity. The device shown on top left is called particle tracking velocimetry. We call it PTV. So in this PTV, they have suspensions of neutrally buoyant particles. And the movement of this neutrally buoyant particle is captured by high-speed camera, so that you eventually end up with some images, something like bottom left. And then if you can identify the positions of the particle comparing both images, then you can approximate the velocity at some locations. And you can imagine, if we use this kind of device, then the measurement we are getting out of this PTV is highly noisy. So the high resolution measurement we can get is something look like top left corner on the right figure. Although we can have some small scale structures, the data is highly corrupted, so it's very difficult to understand what's really going on. And then later, if we change the, say, some parameters such as the length of average or grid space or length of correlations, then you can move from the top left to the bottom right. So at this stage, now we have the much smooth velocity field, but the problem is that now all the high small scale structures went away. So now the question we have is that how can we, what kind of resolution we want to work with, and how can we deal with the noise? So one of the interests is that if we can start from this bottom right corner, that's a very smoothed out low resolution information. And if we can use this information to reconstruct this high scale, very high wave number phenomena, then that's going to be the ideal scenario. And that's where the super resolution comes in. So super resolution is not like a new area. Super resolution has been studied for a few decades now. The classical super resolution problem is actually using a sequence of low resolution images to reconstruct the high resolution data. So when you have some observation function which is fixed, the observation function in this case is denoted by this matrix M, for example. Then this high resolution, the ground truth data is projected on this low resolution image by the observation function. And then as we combine different frames of a moving object, then different areas are captured by this observation function. Then the basic idea is that we can stitch these different information together to generate the high resolution image. So in this example, they actually shows that if we combine these many, like 55 low resolution frames, then they could come up with this high resolution reconstruction of ground truth. But with the development of deep learning now, the idea of super resolution has been changes, that instead of solving optimization problems to reconstruct high resolution information by using a low resolution sequence of low resolutions, now the idea is that we do every of these reconstruction in the training time. So once we have a tremendous amount of training data, then we can actually find a structure from this low resolution image to generate high resolution reconstruction. So that instead of having multiple images now in deep learning time, we are mostly looking at a single image super resolution, that we just give this information, and we want to zoom in to these rectangles and get a high resolution image. So this result shows these super resolutions for this particular area. And this bicubic is just like a simple bicubic interpolation, which is mostly similar to the low resolution data we have. But when you apply this deep learning method, as shown here, the deep learning method provides much more realistic images than the simple bicubic interpolations. So thanks to the success of deep learning in these single image super resolutions, now it has been applied to many different physical problems. In first example shown here, now they went to really extreme. The super resolution problems that people usually looked at is mostly like 4 times or 8 times super resolution. But in this particular study, they looked at a 50 times super resolution problem that they first start from very low resolution image, and then they upscale it to the medium. They have two models. One is that upscaling from low resolution to medium resolution, and they have another model that's upscaling from medium resolution to high resolutions. So that they claimed that if we have these stepwise approaches, they could achieve 50 times super resolutions. And the model was applied to some global scale climate problems. In this case, what's shown on the left is the original low resolution image. And using the method, they can generate the super resolution data shown on the right, which looks much more realistic. But more quantitative study is shown on the right. In this case, in this study, they are looking at the turbulent channel flows. So here, it's mostly like a 4 times super resolution problem. The rightmost column shows the direct numerical simulation, that's the ground truth. And when they supply the low resolution data, which is shown on the left, then their neural network can generate the high resolution data, which looks much more realistic. And what's interesting in this study is that when we look at the energy spectrum of the super resolution results that is shown on here, in this energy spectrum, the black line is ground truth, and the vertical line shown here is the cutoff length, meaning that they generate the low resolution data by using spectral filter, which cuts off all the high wave number information. After the reconstruction, the energy spectrum of the reconstructed field is shown as symbols, which is almost identical to the ground truth. So it means that this super resolution method can actually recover the ground truth, which is generating the images that is very close to the physical phenomena that's happening. But what we actually need to remember here is that even though there was success in applying super resolutions for the physical problems, the super resolution is ill-posed problem, so that you don't really have a unique solutions to match the low resolution data. So there can be infinite number of solutions to match the low resolution data from high resolutions. One example shown here is that on the left, we can have apparently blurred image of Obama, but after the reconstruction, they get someone else. And what's shown here is that they have the very blurred image of some person, and their neural network is generating many different possibilities. And all of these possibilities, apparently different people, can match the low resolution data. So in a sense, super resolution is ill-posed problem. There is no unique solution. So one possibility is that if we have the super resolution reconstruction of a single image to image, then the reconstructed field may satisfy the kinematic conditions. For example, if we have incompressible flows, then it may satisfy the mass conservation. But there is no guarantee that this the reconstruct field satisfies this dynamic constraint such as moment conservation. So there are new studies that comes out. In these studies, the people started looking at the sequence reconstruction. So now we are going back to the classical time of we try to do the super resolution based on the sequential information, and to actually satisfy the dynamic constraint. So in this plot, in this study, what they did is that they are looking at the sequence of low resolution images centered around the high resolution reconstruction they want to have. And then in this plot, the figure on the right is ground truth, and the one left is the multiple time snapshot reconstruction, and the left is single snapshot reconstruction. So it looks almost the same, but the multiple snapshot is a little bit better. So when you look at the statistical properties that is shown here, again, this is the energy spectrum of turbulent flows. The black line is ground truth. And here, this blue line is the multiple snapshot reconstruction. And this red line is a single snapshot reconstruction. So they actually showed that having multiple snapshots to the reconstruction super resolution has a better accuracy than single snapshot to snapshot super resolutions. And this is a study that just came out. In this study, they also have the similar idea that instead of minimizing the error between low resolution and high resolution in each snapshot, now they are proposing to have a time marching error to satisfy the dynamic constraint. And in figure on the right, in this figure, the first column is ground truth. Second column is the low resolution data. They essentially take the scales and get the average inside the scale. And the right columns are super resolution reconstructions using this dynamic loss. And you can see that they are very close with. Okay, do you have a question?
Yes, Doctor. Can you talk about conservation properties like mass, momentum, and energy in these super resolution? Because they are important for incompressible flows.
Yeah, that's actually a very good question. So in this case, that's actually one of the purpose why this author was going into this this kind of time marching loss. To the time marching loss, essentially having comparing the momentum conservations between the ground truth data and the super resolution models to satisfy so that it's likely to satisfy the momentum conservation, but in always that this provides a soft constraint, not hard constraint. So always the issues with this deep learning model is that it's very hard to make the model to satisfy the hard constraints. So it may approximately satisfy the moment conservation, but not exactly. Also, same story goes to the mass conservation. So usually you need to have the actual mass conservation in loss function. Otherwise, it's going to be very tricky to satisfy. Okay, so what are different another question here?
Yeah, it says the Sean is asking, what is the definition for the n theta and variable phi?
Oh, this phi is time marching operator, and u is ground truth velocity. And then here, what it is that this is first C is a projection to the low resolution data, and then n we apply n for the reconstruction, then applying it to the time marching operator. So we first have the ground truth to the low resolutions, and then neural network to reconstruct to high resolutions, and then applying time marching operator and comparing these two. So anyway, the message here is that if you look at this error plot, so this figure, the vertical line is the L2 error, horizontal line is some computation parameters, and this green line is a single snapshot super resolutions, and this red line, this blue line is multi-snapshot super resolutions, and it shows the multi-snapshot super resolutions has smaller errors than the single snapshot, so it has better it has better approximation of ground truth. And what's interesting in this study is that they compare the flow field predictions using the data assimilations and the super resolutions. Data assimilation in this case may use Newtonian nudging. And then what they found is that when there is a noise in the initial conditions, then in super resolutions, the noise in super resolution method, the noise effect of the noise doesn't propagate a lot, in downstream, so that the the noise is quickly removed, while when they use data assimilations, the noise propagates much longer, meaning that super resolution also has some denoising capability. So these studies essentially say that in super resolutions, we want to have some we want to include some dynamic effect, and that's actually what we are interested in this study. So if we simplify the system, now we can simplify the system in this way, that we have the original system that has the equation that has the time matching system of high resolution information denoted by mu h, and then from this original system, now we get the high resolution information that is filtered to generate the low resolution data. And then we have another system that is called observer. This observer system is supposed to have the same equation with the high resolution system. But this observer system doesn't really have the same initial conditions, as well as it doesn't really have the direct information of this high resolution ground truth. We only have an observation of this low resolution information. Then this very simple schematic explains that it captures the essence of this dynamic super resolution problem we are looking at. Then the next question we can naturally have is that when we have very complex nonlinear dynamical system that can be chaotic, such as Navier-Stokes equations, then for chaotic systems, what we know is that even small perturbations eventually make two systems diverge. But in this observer system, we don't see the ground truth of this high resolution information. We only see the filtered low resolution information. Then the question is that when the system is chaotic, whether this super resolution model can really approximate the ground truth or not. And the answer to this question comes from very interesting phenomena called chaos synchronization. So chaos synchronization means that when you have two chaotic systems, sometimes by exchanging informations, these two chaotic systems can synchronize with each other. So this is one of the early examples of chaos synchronization. That on the left hand, we have the original Lossler equations, Lossler system. And on the right hand, we have another Lossler system that is starting from different initial conditions. But what they found is that if we have one of the dimensions of this original system to derive this observer system, then eventually we can get this observer system synchronized with the original system. So that this kind of synchronization of a chaotic system has been studied extensively, and there is a very nice review of this coupled dynamical system in this paper. So this kind of chaos synchronization was actually observed in turbulent flows. So in this study, this is a very interesting study where they have this Navier-Stokes equation, and they use some kind of spatial filter to generate the low resolution data denoted by U1. And then now they have the observer system. This observer system only using this low resolution data and moving in time. What they found is that this delta T is the deviation of this observer system from the ground truth. And then what they found is that this deviation is actually diminishing to the machine accuracy, and the rate of this decay of the deviation is exponentially fast. So that they actually found when the low resolution data hovers up to 10 or 15 times Kolmogorov timescale, then it can this super resolution system can actually recover the ground truth almost exactly. So here the left one is the input data, that's the low resolution data, and the right column is the super resolution reconstruction that really preserve a very small scale characteristics, and it actually converges the original high resolution system. So the same study has been there also has been same study on the chaos synchronization in Navier-Stokes flows, and what they suggested is that this chaos synchronization in Navier-Stokes equations actually occurs over a wide range of parameters, and then they suggested that this chaos synchronization is actually properties of Navier-Stokes equation, not related to specific data assimilation algorithms. So this type of convergence of observer system to super resolution observer system to ground truth has been studied a lot in data assimilation community. So this is one of the old studies that was done by Olsen and TT. This is very classic study that mathematically show proof that in 2D turbulence that this super resolution so data assimilation actually converges to the ground truth. And in more recent studies, they actually mathematical proved also in 2D flows that when you have super resolution models under certain conditions, that this super resolution, the error of this super resolution model decreases exponentially fast and converges to the ground truth system with machine accuracy. So what it essentially says is that when we have a very clean system that is noise that doesn't contain any noise, then super resolution model have the potential to actually reconstruct the ground truth, in particular for the Navier-Stokes fluid. Then let's go back to the motivation in the beginning that we are looking at the system that is not noise free. We are interested in reconstruction of noise observations. Then we have many different behaviors. We have, depending on the filter we are using, we can have many different resolutions. Now we want to have some guideline. What's the resolution we want to work with? And if we use some of these resolutions, whether we have a guarantee of some kind of convergence to the ground truth system. So that so far there are many studies of super resolutions for dynamic turbulent flows and many physical systems, but most of the studies have been empirical. And what we wanted to achieve in this study is to provide some theoretical guideline whether this super resolution model is actually working or if it works under what kind of conditions. So let me now talk about the problem setup of our study. Here we are still looking at two-dimensional turbulent flows. The original system we are interested is that we are using is something called Kolmogorov flow. This is essentially two-dimensional incompressible Navier-Stokes equation. And here the driving force is given by some sinusoidal function, some sine function. And then the computational domain is periodic. So we have 2 pi in both directions. And we use a pseudo-spectral solver with 512 mode in each directions. So in the initial conditions, we randomly generate the initial conditions by seeding a very high wave number vortices. And then as time goes, the vortices evolve to generate the turbulent field as shown here. This plot is time evolution of the vorticity field starting from time equal to 0 to 13. So now we have the observer system. The observer system is same as the ground truth system. So it has it's still Navier-Stokes equation 2D, but this observer system has a different initial condition than the ground truth system because we don't know the initial conditions. And this observer system is coupled to the ground truth by this feedback mechanism. Here, L is some parameter that's related to the relaxation timescale of this observer system to the ground truth. And this C is a low resolution projection operator. And this C is defined as in this equation. Essentially, what this operator does is that we compute average velocity in subdomain denoted by omega j, and then we distribute this average over this subdomain. So if you look at the figure on the right, then this is the total computational domain. Then we divide this total computational domain into a disjoint subdomains. And in each subdomain, we compute the average velocity, and then they distribute this average velocity within this subdomain. So we have a piecewise continuous velocity field in the whole domain. And this observer system is solved by a second order finite element method, so that it has lower order accuracy than the one used for the data generation process. And this operator C should satisfy some of the regularity conditions that is shown here. But I will get back to these conditions later in the talk. And we generate the noise observation. The noise observation is generated by adding white noise to the ground truth. So this is a small y. So this U is a high resolution ground truth. And then we add a random noise, white noise, to this ground truth to have noise observations. And then we apply this low resolution operator C to the high resolution noise observation to generate the data that we are supplying to the observer. So this Y denotes the data. And this figure shows the process that the left figure is the ground truth velocity. And then when we add the noise, the corrupted data looks like the figure on the mirror. And then the low resolution projection of this corrupted data that is we are supplying to the super resolution model is shown on the right. So this low resolution data is of course much less noisy than this high resolution data, but it is also very different from the ground truth because we are filtering out many of the small scale informations. So in this corruption process, we don't actually request this noise eta to be Gaussian, but we assume that this noise has a finite variance, so that we introduce a regularity conditions. This regularity condition means that this integral inside the bracket is essentially a variance of the noise. And this variance of the noise multiplied by some constant is less than 1, meaning that, so we assume that there are some positive coefficient R, which can be used to bound the variance. So as long as the noise is bounded, then this condition is satisfied. Okay. Now the main results of our study is summarized here, but here I'm not going to explain details about these theorems, but essentially what we try to show in this theorem is that when we have this observer system, which is coupled to the ground truth by using the low resolution observation, then this observer system converges exponentially fast to the neighborhood of the ground truth. And when there is no noise in the observation, what is found before was that this G will exactly converge to U. But when there is noise, then then this observer system converges to U, but it only stays in the neighborhood, not exactly converging to the ground truth. So that we have the convergence zone where this perturbed velocity field converges to the original ground truth. And once this observer is inside of this error bound, then it's going to stay there without escaping. So that this convergence zone is globally attracting. So this is here. This is the main result of the study, and let me just briefly sketch what this theorem actually derived and what it actually means. So we first start from the weak form of the Navier-Stokes equation. That here the first line is the weak form of the ground truth system, and the bottom is the observer system. And we subtracted these two to get the evolution equation of the error. So here in this equation, what's denoted by E is the error term, that's the ground truth velocity field subtracted by the observer velocity field. And then the idea of this proof is that if we can find the bound of each of these terms, then we can understand how this evolution equation will behave. So, but I'm not going to explain details about all of the other terms, but what we are interested in here is what happens with something happening in this term. In this term, F is the driving force of the Navier-Stokes equation that's known, and this capital F is the feedback force. So that this capital F is essentially a combination of the driving force with this observer low resolution input. And then if we manipulate this capital F driving force term, now we can decompose it into two terms. One is that we have the projection of the error, and another term is the low resolution projection of the noise. And so that if we look at this term now, we can actually compute the upper bound of this inner product as shown here. And what we are, again, in this upper bound, what we are interested in is only what's happening with this inner product between the noise and the error term. So here, this is actually typo. It should be eta, not psi. But anyway, what we're interested in is only this inner product between noise and the error term. And then the bound of this noise inner product is shown here. So that we first just write down the definition of the inner product, and then we use the regularity condition that we introduced it before to get the bound of this inner product. And at the end of the day, after doing some manipulations, now we can find the upper bound of this inner product in terms of the L2 error. And the coefficient F sigma is defined in here. The sigma depends on the size of the subdomain. This H is the size of subdomain, and R is the parameter that depends on the variance of the noise. So after doing some manipulation, this is again writing down this inner product, and we looked at what's happening inside of this inner product between noise and error. Then we end up with some conditions that we can find some coefficient delta, which is between 0 and 1. And once we have the conditions that this delta multiplied by L2 error is larger than the sigma coefficient from the regularity conditions, then what we can further reduce the temporal time evolution equation of error into this form. And then if we have further conditions that the first term is less than the second term, then we can even simplify the error evolution equation shown here. So what it essentially says is that the upper bound of the time evolution of L2 error. L2 error means that the super resolution reconstruction and the ground truth is bounded, is exponentially decaying function. So we have the relaxation process that the upper bound of L2 error is decaying. And then to get this term, we actually made some of the assumptions that this L2 error is bigger than this coefficient sigma. So in other words, when this L2 error is bigger than right-hand side, then error is decaying exponentially fast. And when L2 error is less than the right-hand side, then we don't know. We don't know whether it's going to decrease or increase, but that's not our interest at this time. So based on these conditions, now we can have the zone of convergence, meaning that when L2 error is bigger than this zone of convergence denoted by here, then it's already exponentially fastly decreasing. So that this zone of convergence essentially provides us the upper bound of L2 error. Now let's look at this upper bound a little bit more closely. So that this is the definition of the zone of error, the convergence zone. Then from the regularity conditions we had before, again, what's happening inside of this bracket is just the variance averaged over the domain. And let's say we have the computational grid or data grid that is shown here, that is high resolution data with grid size delta x. And we have a subdomain that is shown in these red rectangles that have size h. Then we can define a compression ratio. That's the ratio between the size of the subdomain and the grid space. And using this compression ratio, now we can show that the average expectation of this integration inside the bracket can be written as sigma square. That's the variance of the noise divided by c square. That's this compression ratio. Larger C means that we have a coarse resolutions. So using these conditions at the end of the day, we can bound all of these expressions, and we find that the zone of convergence can be expressed by this equation. So that here, this omega is the size of the computational domain, and delta is some parameter, positive parameter we can choose. Then what this equation essentially says is that the upper bound of error is proportional to the variance standard deviation of the noise. But what's interesting is that it's actually inversely proportional to the grid size. So it's very counterintuitive, because when you have the high resolution information, the usual intuition is that we want to somehow work with this high resolution information to get a better reconstruction. But what this research actually says is that if we reduce the resolution of this super resolution system, then we can resolution of the input data to super resolution, we can actually have a better reconstruction. So that this corollary actually summarizes all of the derivations, all of the proof I just outlined. That this figure, the quantity on the left defines of the zone of convergence, and this zone of convergence, that's the upper bound of error, is essentially decreased when the data resolution gets coarser. So here, that's the theoretical results. Now we are trying to show now we are trying to see that if the theoretical results can be observed in the actual numerical experiment. So here we do, so this is outline of the numerical experiment. The original system, the two-dimensional Navier-Stokes equation was solved by the pseudo-spectral method, and we are using 512 Fourier mode to solve this Navier-Stokes equation. And the observer system is now solved by second-order finite element method. And then again shown on the right is the high resolution grid, and we have this subdomain denoted by this red curve. And then the size of this domain is denoted by h, and we have compression ratio that's giving us the ratio of super resolution. And the noise magnitude here is that the variance of noise is proportional to the turbulent kinetic energy. Turbulent kinetic energy is defined on here. And then we looked at the different parameter range, that the viscosity changed from 0015 to 009, and then different noise levels and different compression ratios. Okay. And the actual code is you can find the actual code in this GitHub repo. So this is open source code. You can download and test it. So this is the results of the velocity reconstruction for the parameter range shown here. So then now we are looking at the compression ratio of 32, meaning that we are looking at 32 times super resolutions. So this is the ground truth state in the initial condition of ground truth state, and we superposed noise to the initial state. And then this is the low resolution input data that is averaged by 32 by 32 grid. And then the right figure shown here is a super resolution reconstruction. But initial condition of super resolution reconstruction is just like almost 0 in this case. And then after some time here, we are looking at t equal to 8. Then figure on the left is ground truth, and we have the corrupted data. And then eventually the reconstruction shown on the right is very close to the ground truth. And the figure on the middle is the actual low resolution data that was supplied to the super resolution models. So that if you look at the figure on the bottom, then the left one, this is the velocity field in the center of the domain. This is the horizontal velocity at the center of the domain. And you can see that this is the ground truth, and this is the low resolution data, and super resolution reconstruction in this case becomes very close to ground truth, even though low resolution data doesn't really have these high small scale structures. So this figure shows the reconstruction error at one time. This is a snapshot. It's the same snapshot at t equal to 8. And here we are looking at the error field at different compression ratio. Compression ratio 1 means that it's like a data assimilation algorithm. And then we apply the super resolutions. Then as you can see here, that as we increase the compression ratio, then the error gets smaller and smaller. And in this case, if you look at the color bar changes from 0.1 to -1, while the color bar of the ground truth changes from 2 to -2, so that the error range here is much smaller than the actual velocity field. And this is consistent with the study that I explained in the beginning, that when you had where they found that the super resolution models have very strong characteristics in the denoising very strong denoising capability, and we also showed that when you use super resolution, the error becomes much less than as you increase the size of the subdomains. And now we are looking at the convergence of this super resolution. The relative error in this case is defined by L2 error divided by the velocity fluctuations. And the reason is that based on the definition of the zone of convergence, and the definition of this variance of the noise. Now, what we can see is that this relative error should scale as the convergence zone, like it should decay as the compression ratio. So if you look at this case, so both of them are from same noise level 1.6 at different viscosity. What you can see is that so this line is the C equal to 1, meaning that there is no compression. And as we increase the compression ratio, the super resolution ratio, then we see that the relative error actually decreases. And then in the beginning, we also starting from different, we are starting from zero velocity field. So we have different initial velocity than the ground truth. And the deviation from the ground truth decays exponentially fast. So that is consistent with the theoretical predictions. But another thing we observe is that as we increase the size of subdomain, the super resolution ratio, then it first decrease, but then eventually when we decrease when we increase super resolution ratio further, then the error starting to diverge. The system starting to diverge from the ground truth. So that it's first decreasing and it's going up to here. That's because in theoretical predictions, we have some necessary conditions for the convergence, that the size of the subdomain, the ratio of the super resolution, should be bounded by some constant multiplied by the viscosity, which is inversely proportional to the Reynolds number. Now, for the interest of time, I'm going to skip this figure and just going to explain about this last figure. So in this last figure now, this is actually summarization of all the experiments. Here we are looking at 3 different viscosity. And the vertical axis is the relative error. Horizontal axis is the super resolution ratio. And different color means the different noise level. So that going from top to bottom, we have noise from noise level changing from 1.6 to 0, so that the line on the bottom is actually noise-free super resolution case. So what the first thing we notice is that if you see the figures, the line here is C to the minus 0.5. So we actually see that when we increase the compression ratio, the error is error decreases, but the ratio that error decreases is actually much slower than the theoretical predictions. In theoretical predictions, we predicted C to the minus 1, but in numerical experiments, we have C to the minus 0.5. But one reason that we have slower convergence is because of because we are using a low order CFD solver for the observers. The ground truth was generated by spatial method, while the low observer was solved by second order finite element method. The reason we use a low order CFD solver for the observer is that we want to mimic the real life scenario where we don't really have that kind of high resolution info. We don't really have that kind of high fidelity models to reconstruct the velocity field. So if we use like highly accurate pseudospectral method, then this this noise-free reconstruction should going further down here, so that it actually should converge to the ground truth with the machine accuracy. But instead, since we are using low order solver, we have the finite error, and this finite error may contribute to this slower decay of the error we observe in numerical experiments. And another observation is that as we increase the compression ratio and as we reduce the viscosity, then now the relative error first decreases, but it's now starting to increase as we increase the super resolution ratio C. So it's because as we in smaller viscosity, we have more strict regularity conditions. And then if we use higher compression ratio, then eventually we are violating the necessary conditions for the convergence. Now we finally get to the conclusions. So in conclusions, what we have done is more like a theoretical analysis of super resolutions. We try to provide some guidelines or theoretical understanding why the super resolution works, or if the super resolution of this complex system actually works. So that and what we found is the counterintuitively, this theoretical analysis indicates this decrease of estimation error. That was very interesting. But one of the, so in this summary, the most interesting part is the last item, that there is a limitations of the current study, because the theoretical analysis is mostly limited to isotropic flows, and the estimate we are getting is very conservative, meaning that the error bound we provide as a zone of convergence actually should be much larger than what it should be. So we it's actually for the follow-up study that we are looking at, then how can you expand the current analysis to more complex flows, such as some inhomogeneous turbulent flows, and how can you get a more sharper error bound than what we currently have so far? So thank you for your attention, and this is the end of the talk.
Thank you. Thank you so much for the wonderful talk. Very fascinating. Awesome. Let's have a Q&A sessions. Okay, so there are some questions in the chat room by Sean. I think he already left, but he said, thank you for the nice talk. Perhaps a missing reference from Tama he was sharing. So there's a link for the paper,
Okay.
and he wanted to share with you.
Mm-hmm.
Okay,
Great.
the next question is by Kevin. He is asking, what's an intuitive explanation for the increasing accuracy with coarser mesh? While measurement noise is smoothed out by coarser mesh, high frequency flow features can be preserved by observer flow model?
Yes, that's actually a very, very good question. So that one is that we are smoothing out by using this filter. Naturally, we are smoothing out the noise. Then that's good. But also, we are smoothing out the small scale features together with the noise. So that the question is that there is a balance that, and so that even though we are smoothing out the small high wave number features by using this observer, in Navier-Stokes equation, we have some kind of there is energy cascade is happening. That is energy is cascading from large scale to small scales, and when we have when this when this energy cascade happens at a certain scale, less than certain scales, then we can actually recover all these high scale phenomena. That's actually what we found in this study. That even though we don't have information at very, very small scales, say that even though we filter out all the information about 10, 15 times common scale, we can actually recover all of these missing information. We can exactly recover all of these missing informations by through the energy cascade. So that now the what we try to looking at is actually a balance between these two. The one is that we are having filtering effect, but if we filter too much, then we cannot recover the ground truth. So that we are looking at we try to get a theory that how can you have the balance between these noise filtering effect as well as the reconstruction of the ground truth?
I think your error bounds analysis is kind of showing that story as well, right?
Yes, exactly. So
The
that
coarse mesh shouldn't exceed certain upper bounds, otherwise you cannot recover the high frequency.
yeah, so that that's why we have this
Yeah.
we have noise, we have this necessary condition, and this new is viscosity. Essentially, the right-hand side defines the dissipation rate, so that it's related to the Kolmogorov scale in turbulence. So that should be that's the super resolution ratio is a function of some Kolmogorov scale.
Yeah,
Probably, but we actually looked at 2D, so that's also one of the limitations of the current study.
I see. Okay, already fascinating for the 2D. Next question is by Dave. Thank you for a very interesting talk. Your examples were for 2D turbulence, where the energy naturally flows from small to large scales,
Yeah.
inverse cascade. How would your approach work for 3D turbulence when the energy flows from large to small scale?
That's a good question. That's a very good question. We frankly speaking, that's actually why I had the last item in the conclusions that we certainly admit that there are the limitations of the current story, and because of the lack of mathematical tools, we usually cannot. It's very hard to go to 3D to actual proof of convergence in 3D turbulence. But what we have seen is that there is some physical explorations about what's happening in 3D flows. So in this study, they actually showed they have some theoretical derivations of the say critical length scale to recover the high resolution information. So we believe that the similar behavior can be observed in 3D, but the actual mathematical proof of convergence is still a long way to go.
Okay. All right. Next question is by Shima. Thank you so much for such a great talk. I really enjoyed it. I'm also curious about 3D turbulent flow, which is more important. Okay.
Yeah.
But
Yeah.
pretty much same
Thank you.
question. Okay.
We are working on it, but it's tricky.
It takes time. Everything takes time. Understand. That's awesome. Okay, so I guess I can ask questions related to the Fadi's questions in the beginning. You know, preserving those conservation of law or some physical property. That's still challenging
Yes.
to accomplish, right?
Right.
Okay.
So the deep learning models, always the tricky part is that how can it make a input, incorporate hard constraint is always the tricky part. So that we have like many feasible solutions, and we want to reduce the space of solutions that is actually not mathematically feasible, but physically feasible. But that process is still open question, I believe.
Yeah. But still, I mean, the work you have presented today is very impressive already.
Thank you. But yeah, thank you.
So I keep up the good work. I think it's we can wrap up the seminar today. Let's thank our speaker for the wonderful talk, and through this opportunity, and we can establish some collaboration between Lawrence Livermore and your group, and in the
Sure.
future we can do greater things together. Let's hope for that. Thank you so much for the wonderful talk.
Thank you.
Yeah. Okay, that concludes today's the seminar.